Hello to all my friends in YouTube land. We're going to have a calculus session in today's video, and specifically we're going to check out trying to find the volume of the resulting three-dimensional object that comes about by revolving a two-dimensional planar area, namely the one that I'm sketching out right there, about a line or an axis, namely in today's video, the axis or the line y equals 3, shown there. We're confining this region to the interval 0 to 1, as shown right over here on the x-axis. The place where these two graphs meet is up on the y-axis at the value of 2. The graph on the top is the linear graph, y equals 2x, so as the name suggests, linear. It's a first degree order curve, and it is a straight line, in fact. It's a line with slope 2. The graph on the bottom is that of a parabola. It's the parabola y equals 2x squared. We're going to use two popular methods to do this. You're probably taking this in your calculus class presently. One is the disk method, and then part B will illustrate solving the same exact problem using the shell method. All right. I'm not going to attempt to draw out the resulting three-dimensional object when you revolve that planar area about the line y equals 3. That would be awfully complicated. But I am going to ask you to see that in your mind's eye. Speaking of seeing, let's check out something from Scripture. I'm reading from the first epistle of John, chapter 4, verses 20 through 21, reading from the English Standard Version. It says, "If anyone says, 'I love God,' and hates his brother, he is a liar. For he who does not love his brother whom he has seen cannot love God whom he has not seen. And this commandment we have from him. Whoever loves God must also love his brother." So my short commentary for today is to give you a little food for thought. How about all these so-called brothers who are killing brothers in the name of religion? Wouldn't you agree that they are all a bunch of liars? A little food for thought there for you, my friends. All right, let's get right into the mathematics. So, part A, disk method. As the name suggests, we're going to involve a disk. So let me go ahead and start drawing out for you a disk here. Here is a disk, or perhaps a washer, maybe another name that you may hear about it. And this washer has a differential width of dx. Here is that line that we're spinning this about, y equals 3. And if I extend the bottom of this disk out here, where it intersects the bottom graph, I have this little differential piece that has a width on the bottom of dx, okay? So that's like that right there, okay? Actually, on the inside, it's going to be like this, okay? Alrighty, so now what I need to do is try to figure out what is the area of this washer part. If I can figure out what the area of this washer part is, then I multiply it by the differential width on the bottom, and I'll get my differential volume. And once I have my differential volume, I can integrate both sides, and I'm in business. So the first question that we need to try to answer is, what is the area of that washer? I think we all know how to do that. The area of the washer is the area of the entire disk. So let me call that A outer. So that's the entire disk without the donut hole in the center, less the donut hole in the center. Let me call that the A inner part. Well, what is A outer and what is A inner? Let me do these in different colors so you see it. A outer is going to be the radial dimension. R outer is the radial dimension going from obviously the center of that all the way to the outer part of that disk. And the R inner part is going to be the radial dimension going from the center to the inner part of that. And now the question is, what are these guys? Well, I think it's pretty obvious to say that R0 is going to be all of this dimension 3, okay, minus the bottom part of that. The bottom part of that is where you have the bottom graph, so it's going to be the 2x squared part. If I say 3 minus 2x squared, I'm going to get the outer radial part, and so that is that part. So I'm going to have our outer is 3 minus 2x squared. And by a similar way of logicking that out, you're going to have our inner being all of 3 minus the top part of the graph, which is 2x. So now we have expressions for the inner radial part as well as the outer radial part. And all that remains to do is say, well, what is A0 and what is AI? The outer area and the inner area. This is pi times r outer squared minus pi times r inner squared. I can factor out a common pi between these two. I get pi times the expression r outer squared minus r inner squared. And now I can say, therefore, over here on the left, I can say that my differential volume is equal to the area times the differential width, right? Okay, so this is going to equal A is pi times R0, we said in the pink over there, is 3 minus 2x squared, and that's being squared, minus the R inner is 3 minus 2x, and that's being squared, times the dx portion. Notice that x is running between 0 and 1 as stated in the problem's interval. Okay, so that's the interval of interest here. Okay, so to do this problem is actually pretty simple. We need to integrate both sides of this. So on the left we have dv. When I integrate dv on the left, I just get v, which is what I'm interested in. I'm interested in the volume. And then on the right I get pi, which comes out of the integral because it's a constant. And now I get the integral as x ranges between 0 and 1 of all of that stuff. Now, to make this go a little bit faster, let me go ahead and multiply this 3 minus 2x squared expression, which is being squared. Let's do that up here. Let's see what that is. So 3 minus 2x squared being squared is 3 minus 2x times 3 minus 2x, those squared, I should say, expressions being squared. So you get 9 minus 3 times minus 2x squared is a minus 6x squared, and then minus 2x squared times 3 is another minus 6x squared, and then minus 2x squared times minus 2x squared is a plus 4x to the fourth, right? So in the first case, we're going to get, if I write the highest power one first, it doesn't really matter. I'm going to get 4x to the fourth power, right? Then I get a minus 12x squared in the middle part, plus a 9. Okay. And then I've got minus, let's do this one in our heads, okay? We've got a 3 minus 2x expression being squared, so that's going to come to a, let me say, a 4x squared minus a 12x plus 9. And then out here we have dx, okay? Let's see if we can clean that up a little bit. We get v is equal to pi times the integral 0 to 1. We get 4x to the fourth. We get a minus 12x squared, and then we have a minus 4x squared, so that's going to be a minus 16x squared. And then we get a plus 9 and a minus 9. Those wash out, but then we also have this minus times the minus 12, so that's a plus 12x. So there you have it. And since every term involves an x, especially even when we do the integration, we're going to retain only x's. That bottom limit of 0 isn't really going to come into play here. Right, so let's see what we get. We get, when I do this, I get a 4/5 x to the 5th power minus a 16/3 x cubed plus a 12 divided by 2 is 6x squared. And this is evaluated between 0 and 1. And like I said, the 0 is really a wash on the bottom. The 1 is also kind of a wash in the sense that all I'm going to retain are the coefficients there. So we get pi times the expression 4/5 minus 16/3 plus 6. And let's see, what is that? That is equal to pi times, let me bring out a 15 on the bottom. So that's going to be a 3 times 4 minus a 5 times 16 plus a 15 times a 6. Alright, and if I'm not mistaken, this is going to be 3 times 4 is a 12 minus 5 times 16 is a 80 plus 15 times 6 is a 90. Alright, and let's see, that's pi over 15. 90 minus 80 is 10. 10 plus 12 is 22. And so we see that the volume is 22 pi over 15 cubic dimensions. Or it might be cubic meters, cubic centimeters, cubic inches, or cubic feet, whatever it may be. So by the disk method, we've shown that the volume works out to 22 pi over 15. Let's see if we can't get the same exact answer by using the shell method. So let's check that out real fast. Alright, so for the shell method, as the name suggests, once again, we're going to get a shell out here. Let me draw a picture of the shell. Here is a shell. I'm going to exaggerate this shell greatly. Right? So greatly exaggerated shell. And what we're interested in looking now, let me do this in a different color. Let me do it in red here. We're interested in seeing what is this differential strip sitting down here, which again, if you bring this back, is going to be this piece here. So that's why I said it's greatly exaggerated, because it should only really be this wide, in fact, okay? But I'm making it this wide. Okay, well, we first of all note that this dimension right in here is the dy piece. It's the differential y dimension. And now I need to know what is this length of this so that I can actually find my dA, the differential area of that strip. Well, I believe you would agree that the length of this guy is going to be the rightmost dimension minus the leftmost dimension. So if I take the rightmost dimension, it's corresponding to this graph. However, one thing I need to point out before we move forward is that we're really anticipating an integration with respect to the variable y. So I really need to, before I get much farther, I need to solve this bottom graph x in terms of y. So if I do that, I'm going to find that x is equal to radical y over 2. And likewise, I need to do that for the top graph. So if I solve x in terms of y, I get x is equal to y over 2. And so really, this dimension that I was interested in, the length of that shell, is going to be y radical y over 2 minus y over 2. Okay, that's that length. So the dA is going to be the length, radical y over 2 minus y times the differential height of that, which is dy. That's my dA. Now the other thing I need to do is say what is, now as I spin this differential area about that line y equals 3, I'm generating my shell. So I really need to find out what is my average radial dimension. Let me call that Rav. Okay, so that when I spin it about, I'm going to get my differential volume of that shell. So my differential volume of the shell is going to work out to being, let's do that. We get d volume is equal to the average circumference. Okay, let me write this out here. This is the average circumference times the dA. Okay? Well, what is the average circumference? That means that dV is equal to 2 pi times R average times the dA. Alright? Well, we know what dA is. we know that it's going to be 2 pi r av dA we just said is equal to radical, the expression radical y over 2 minus y over 2 times dy. Y is now running between the limits of 0 and 2. It's 2 up there. Okay. So we get, now the one question that remains is what is our average? Okay, so our average, you might say, let me do this in pink. Well, what is this height right here? What is this height right here? In terms of y, it's just y. Okay, it is whatever y is. It's a variable dimension. So y is ranging between the bottom where it's 0 all the way to 2 at the top, but anywhere in between it's just the variable y. So our average is going to equal nothing other than all of this piece, which is the 3. Okay, so it's going to be 3 minus the y is going to give me the R average. Okay, so the R average, which is that part right there, is, let's put it all together. Okay, so we get, we have d volume is equal to 2 pi 3 minus y times the expression radical y over 2 minus y over 2 times dy. Now I need to do the same old thing that we did in the one above. We need to integrate both sides of that. On the left I get the volume, which is what I'm interested in. 2 pi is a constant. I'm integrating over the range y equals 0 to y equals to 2. And then I have this that I need to FOIL out. Let's go ahead and FOIL it out. I get 3 over radical 2 times radical y. Let me write radical y as y to the 1/2 power. Okay, that's multiplying this with that. And then multiplying this with this, I get minus 3/2 y. That's painless. And then we do this part. We're FOILing out again, so we get minus y times y to the 1/2 is going to be, and then there's a radical 2 over there, so we get a minus 1 over radical 2 times y to the 1 power times y to the 1/2 power is y to the 1 plus 1/2. That's y to the 3/2 power. Right? And then we get, for the last one, we get this piece multiplied by that. That gives me a minus times a minus is a plus y squared over 2. And of course there's our beloved differential y sitting way back there. And now I think this is not too bad to integrate actually. So we get v is equal to 2 pi. Let's do the integral. So we get 3 over radical 2 times y to the 1/2 plus 1, that's 2/2, so that's y to the 3/2, and then we divide by 3/2 or multiply by the reciprocal, which is 2/3, minus 3 over 2, y to the 1 plus 1 is 2 divided by 2, minus 1 over radical 2, and we get y to the 3/2 plus 2/2, which is 1, so that would be y to the 5/2 times 2/5, and then plus y cubed over 2 times 3 on the bottom, that's y cubed over 6 on the bottom, and this is being evaluated as y ranges between 0 and 2. Alright, we're getting there. We are getting there, folks. So volume is equal to 2 pi. The 3's cancel from the top to the bottom over there. And I get an expression 2. Let me rationalize the bottom radical 2. So I get 2 times radical 2. Okay, so I've got that radical 2 times radical 2. You'll notice that radical 2 over radical 2 I'm multiplying by 1. So I didn't change anything per se, but I'm rationalizing that radical 2 on the bottom, so we get that that's going to be what? 2 times radical 2, and then on the bottom, radical 2 times radical 2 is a 2, so this 2 cancels with those guys, so I'm really effectively just getting a radical 2 sitting over here. Right, so I get a radical 2 y to the 3/2 power minus a 3/4 y squared minus a radical 2 over 5, if I rationalize that, y to the 5/2 power plus a y cubed over 6, again evaluated as y ranges between 0 and 2, and we're almost there, we're getting there. This is 2 pi again. Notice that there's a y in every single term, so the bottom limit is a wash, and we just get radical 2, and then we get, would you agree that this y to the 3/2 power, I can write this as y to the 1/2 power times y to the 1 power, or I can write this as y times radical y. Okay, so I'm going to write this as 2 times radical 2 when I stick in the upper limit 2, minus 3/4 2 squared minus, okay, once again this y to the 5/2 power I can write as y to the 1/2 power times y to the 4/2 power, which is radical y times y squared. 4/2 is 2. Right, so I get a radical 2 over 5 times a radical 2 times a 2 squared plus I get a 2 cubed over 6 from that term right over here. Okay, now it's a matter of evaluating all this. So what is this? So we get radical 2 times radical 2 is equal to a 2. 2 times 2 is a 4 minus a 4 divided by a 4. This 2 squared divides with that 4, so we get a minus 3 from that term. Then we get a radical 2 times a radical 2, that's a 2. 2 times 2 times 2, that's 8. So we get a minus 8/5, and then plus an 8/6. Alrighty. And let's hope this works. Let's see. By the way, 8/6 can be reduced. So I get 2 divides 8 4 times, 2 divides 6 3 times. Let me pull out a 15 on the bottom like we did last time. So we get 15 times, before I do that, 4 minus 3 is a 1, so I get a 15 from that. Okay, 15 times 1, if you like, minus a 3 times that 8, okay, from this term, plus a 5 times a 4, alright, from this term. Okay, what is all of this? So hopefully it's going to match. We get 2 pi over 15, 15 minus 24 plus 20, minus 24 plus 20, what is that? That's minus 4. 15 minus 4 is an 11. 11 times 2 is a 22 pi over 15. So once again, we see that our volume is 22 pi over 15. And that's all she wrote, my good friends. I hope that was helpful to you to see two different methods, doing by the disk method as well as the shell method, to come to the very same answer. Well, write me if you have any questions. I went through this rather quickly so that we can get through all that material, but hopefully that was of value to you and you learned something. I hope to see you all in a future video, and don't forget to love one another. Alright, take care. Bye-bye now.